The Raspberry Pi is built around modern 64-bit ARM processor. To successfully write and run assembly programs on this platform, it's important to understand how the processor, architecture, operating system, and compiler work together. Raspberry Pi uses an ARM v8.2a CPU, which supports the AArch64 instruction set. This means that assembly code must be compiled for a 64-bit environment. Although Raspberry Pi OS can start in 32-bit mode, this can lead to compatibility issues when working with assembly. To avoid these problems, the operating system should run in full 64-bit mode. This can be verified by checking the system configuration file. If the parameter ARM64-bit is set to 1, the system is running in 64-bit mode. If it's missing, it can be added manually. Once the operating system is correctly configured, the next step is choosing a compiler. There are two main assembler options available on Raspberry Pi OS. The first is GNU Assembler, commonly used through the GCC toolchain. The second option is LLVM Assembler, which is accessed through Clang. Although Clang itself was not originally designed for assembly, LLVM includes an integrated assembler that fully supports ARM and ARM64 architectures. Both toolchains can be installed directly on Raspberry Pi OS using standard package manager commands. Assembly source code must be saved using a .s or .S file extension. For better organization, it's recommended to create a separate folder for each project. This folder typically contains the source file, the compiler object file, and the final executable. The build process consists of two main steps. First, the assembler converts the source file into an object file. This object file contains machine code, constants, and text data. Second, the linker combines everything into a single executable binary. The resulting file follows the ELF format and can be executed like any other Linux program. Once compiled, the program can be run directly from the terminal. When a program is executed, the Linux shell calls the kernel. The kernel reads the executable file, loads it into memory, and prepares the stack and sets the program counter. Execution begins at special label called _start. In pure assembly programs, this label is mandatory because it defines the entry point for the operating system. Instead of returning like a function, the program must explicitly tell the kernel when to stop running. This is done using a system call for program exit. Without this step, the program would terminate incorrectly. Not all programs rely on an operating system. Bare metal programs run directly on the processor, without Linux or system calls. They execute immediately after system reset and are responsible for hardware initialization, memory setup, and stack configuration. This approach offers higher performance and full hardware control, but it also requires deep knowledge of the processor and peripheral address space. Bare metal development is commonly used for bootloaders, firmware, and real-time systems. Whether you are compiling assembly code as Linux user space program or writing bare metal software, understanding the execution mode and toolchain is essential. With the correct OS configuration and compiler setup, Raspberry Pi 5 becomes a powerful platform for low-level development.